and he's gonna give us a talk of uniformly expanding full branch maps without fixed.
With attractor.
With a trunking fixed one, sorry, I don't understand that. Okay, thank you very much, Rubio, for being here.
Okay, so hi everyone, happy to be here. Thank you for inviting me. I'm Rubio from the ICTP. I'm a student of Stefano. My main interest is embryonic theory, so it's a bit different than the average topic here. But I hope we can all see some cool dynamics today. And my favorite method of research, well, maybe I shouldn't call it my favorite because this is my second year and this is my first result. It's not even published yet. But my favorite method is to construct bad boys. I like to construct examples and counterexamples to certain things that have, well, some people will call it pathological properties. So yeah, I like to construct bad boys. Today, because we have such a short time for lunch, I'll try to keep it short and entertaining. I'm gonna structure this talk a bit like a murder mystery. So I'll start with a bit of introduction, and then I'll show you, oh, this is the killer, and then I'll show how we catch and figure out that he is the killer. So, introduction, let's start with full branch maps. I assume most of you are pretty familiar, so let's be kind of quick. So, full branch map is some self-map from the unit interval itself with a partition of intervals. A partition can be finite or countably infinite. I'll just write it like this, and if it's finite, just imagine the other, that the higher indexes are empty sets. That's a bit of abusive notation, but that's fine. And then we want that the F to map the interior of each interval to the whole unit interval as generally as a homeomorphism, but for we can have it as a C infinity diffeomorphism. And my last assumption is uniform expansion, which is that the derivative, wherever it makes sense, has to be uniformly bounded away from 1. Or if not at the first iterate, it can also be the derivative of a higher iterate. So these are just a bunch of assumptions that I assume some of you have already seen, but just in case, let's refresh with a few examples. So there's the good old doubling map, the 2x mod 1, doubling map on the interval. And there's also the Gauss map, the Gauss continued fraction map, defined by 1 over x, 1. And I'll draw some quick sketches of what they look like. And for the Gauss map, a bit more difficult to draw, but should be something that has infinitely many of these convex branches that get steeper and steeper. So, these are 2 examples. Let's cover a couple of facts about them. What the entropy, the topological entropy. This one has entropy 2, and this one has infinite entropy. And then they are also conjugate to some shift space. So the 2x mod 1 is conjugate to the shift on 2 letters, to the left shift on 2 letters, and this one is conjugate to the left shift on infinite letters. It's a bit of abusive notation because there's like a couple boundary points where it's not really well defined, but for now let's keep it like this. And this conjugation is defined by what we call an itinerary. So for each point, we can associate a sequence, and each sequence is like, which interval does it visit? So if it visits in its orbit, so if it visits here, the 1 and then 2, 2, 2, 2, your sequence would be 1, 2, 2, and that each sequence defines a point, each point defines a sequence. Okay, this is cool. Is there anything else, anything Like there are basic facts I want to review, maybe not. But, so, some of you might be wondering, a full branch map, what the hell is it talking about? Because like, there are already some pretty well-known results on full branch maps. There's something called the folklore theorem, where if I have these assumptions, uniformly expanding, and it's infinity, and if I have finite branches, then for almost every point, we have the time averages of, so you take Dirac delta, centered at each point in the orbit, and we take the orbit from time 0 to time n-1, take the average, and then this will converge to some measure, which is absolutely continuous, invariant, ergodic, equivalent to the bank. And also, other than finite branches, you can also have this if you have something called bounded distortion, which is when, so a form of bounded distortion is when the second derivative divided by the first derivative squared, and you take the supremum over all pairs of points, and if this is bounded, you have some sort of bounded distortion that also guarantees this result. So if you're not super familiar with ergodic theory, it basically says that, well, since this measure is equivalent to a bag, then an average point will just spread around the space, kind of evenly equivalent to the bag. And there's like some stuff about this, statistical properties, correlation, correlation. But these are like the good boys of the full branch maps. And as I said, I don't like good boys, I like bad boys. So let's forget about this scenario and let me ask you a kind of silly question. Can a full branch map have a point be an attractor? Uniformly expanding full branch map have a attractor at a point. So seems a bit silly because locally everything expands. Everything has derivative uniformly bounded away from one. So locally the points will get away from each other. But it turns out you can. My result says that you can have a full branch map satisfying all these assumptions, uniform expanding, C infinity, but you have almost everything attracted to a point. So this is the part of the murder mystery that I showed the dead body in the killer. There we go. Theorem. There exists F such that the basin of 0 is equal to 1. And the basin of 0 is the set of points whose orbit converges to 0. Okay. A bit hard to believe, or maybe not so hard to believe, but you're a bit unsure about how it works. So let me explain how this works. So first let's construct the F, and then later I will explain why and how does this F work. So we define our branches to be the endpoints 2 over 3 to the n plus 1, and 2 over 3 to the n minus 1. So I already prepared some of the points here. So this is I1, I2, I3, and the endpoints are 1, 2 over 3, 2 over 3 squared, 2 over 3 cubed. And okay, so that's IM. And then I want to introduce a new notion, which is there is a subinterval. At each branch we have a subinterval. And I want the map of the subinterval to be the union of the branches to its left. So it's a bit tricky when written out, but I think I can draw it better. So take the first subinterval, take the first branch, that is the subinterval, and then it maps to the left. So if you draw a diagonal to help us, this is pretty much what I'm talking about, the left subinterval. And we have it for every branch. So I'm just gonna draw 3 of them because I'm not a computer who can draw more branches. Okay, 3 of the subintervals in blue. And then for the remaining part, we just complete it in a way that, well, so that it's still C infinity. So this one, that part doesn't matter too much. Now, I have so this LM exists for every full branch map. It's nothing special for now. But now I'll make it a bit, I will add some restrictions to it. Yeah. So I will define Pn to be the proportion of Ln to Im. Okay? So we have these subintervals on the left, we have these proportions, and I will define what I call the, is this readable, this corner?
Yeah, that's fine.
Okay. So the FSSP condition requires 2 things. It requires the product of Pn to be positive, so it's greater than equal than some capital P greater than 0. And then the rest are just some requirements that will make sense later. I also want the sequence to be increasing. And I also want the F, each branch to be convex. So, how to map? We have this condition, and let's do a quick check on the expansion. Because I chose 2/3 because now this branch, the length of this branch is exactly half of what's on its left. Every branch has length exactly half of what's on its left. So the derivative everywhere must be greater than 2. Because this part, which is shorter than this whole branch, maps to something which is as long as twice the branch. So we have uniform expansion. So this map satisfies all the assumptions for F. Now what remains to be checked is what's the measure of the basin. And before we jump into the set, I want to look at this map from purely intuitive level, without technicalities. So imagine you're a point, and you're on this map. You're on some branch. What is the probability of going to the left on that branch? So, or at least, what should be the probability? Like, I don't need a super exact answer, but if I was a point in Taiwan, the probability of me going left is exactly this length over this length, right? So the probability of me going left is P1. So, and then if I was here, going to the left, probability is P2. So what is the probability of being a point that keeps jumping to the left all the time? Well, it should be P1 times P2 times whatever, which is exactly our product P. Did I write? We should have written it equal. So that's the intuition on why the set is positive. It's not the formal argument, it's just, I'm not, if this is not convincing, it's fine, it's just the first idea that I got before I started going through the details. Okay, so we have our introduction, then our function, which is the result. Now let's dive into a bit more detail on how the argument works. So I'm gonna put this down, put that up. It's a bit tricky. Well, okay, it's fine. I'm going to erase everything except the itineraries at the end, because at this stage only that thing matters. So I'm going to define a set called C. And a point belongs to C if its itinerary is strictly increasing. So C stands for increasing, or if you're Italian, for crescente, which I think makes sense in Italian, but not so much in English. But so the set of increasing itineraries, one obvious fact about this is that it belongs to the basin of zero, right? Because if you're at the branch with a higher index, that means you're closer to zero. So, and then another thing about this C is that we can construct C as the intersection of nested set Cn, where Cn is the set of points whose itineraries strictly increase up to time n. So we have a set in the basin, and so C is now a nested intersection. And these sets are a bit easier to draw. I'm going to draw the first couple iterations of Cn. So C0 is just the whole thing. And then C1, when you take some branches, let's draw just the first 3 branches. The L of each branch is exactly the points whose itineraries increase. So C1 will look like this. Just L1, L2, 3. I can draw again C2. For C2, so this is a bit tricky, but this part maps to this thing. So what you want to do is take the preimage of this that lives in this. So if I draw it, it would be like, I put a bunch of holes and each connector component. Well, it's a bit of a rough sketch, but basically this part will map to this and this part will map to this and this and this and this, plus they're too small to draw, and so on and so forth. So these are nested sets, and each of them has measure, this one is measure 1. There's some technicalities on how exactly to compute the measure, but just starting on this C1 has measure P1, and then this one has measure P1 minus P2. So we can conclude that the intersection will have measure capital P. So we have a set with positive measure living in the basin. And to find full measure, we can just, one more remark about this set is that C is also metered, because in the process we remove some open intervals at each step. So C is probably an example of a fat contour set, or at least contained in a fat contour set. It's meager and it has positive measure. And to get to full measure, we can simply just paste the preimages of C everywhere, and you get a full measure meager set. I like to call it P, the set of points where there exists a time such that after that time, your itinerary is strictly increasing. So E for eventual, and so we now know that C is full measure, C has positive measure, and then E, the set I obtained by pasting the preimages of C, will have full measure. So it's it's a full measure meager set that lives in the basin of zero. What else do I want to say? Well, maybe some remark on this is, remember that I erased it, but the topological entropy of this system is still infinite. So I think it's a particularly nice example of a system that's ergodically, almost everything does this very trivial thing of going to zero, but there's still infinite topological entropy in this system. Another thing I want to mention is that the set C and E also exist in other full branch maps like the Gauss map, but their measure is typically zero in most cases. Yeah, I think that's all I wanted to say. Are there any questions or remarks? Sorry, that's not my job.
Okay, thank you very much. Are there any questions?
Sorry, that's the.
So this one is distributive. Okay. Isn't there
Ergodic, like, as in.
some things, almost every can still be sucked into this attractor, but it can still be ergodic at the same time. If you look at the definition, ergodicity does not preclude that you have an attractor. So, do you converge to an attractor, to this attractor in a ergodic way or not?
Well,
I came across these questions and I tried to answer them as one of my own papers, not about this, but where you have a wild attractor in most maps, where you take a weird canter attractor, and then you can ask is it ergodic or not, and also if it's exact and not, but I'm just starting with this. There's still some ergodic questions to ask about when you have an attractor. So ergodicity is like the first.
Can you remind me the definition of ergodic as a
Is if you have a set of positive measure, and it is invariant, does it have to be, and then I mean forward and backward invariant, does it have to be the whole set?
But like ergodic with respect to which measure of the marriage? Okay. Well,
I mean, you don't have to
But
answer
like
it,
this-
but this is like an interesting question. I mean, just suppose that you would have a C plus and a C minus, and C plus you only take the even ranges, and the C minus you only take the odd ranges.
yeah, maybe.
And these sets are different points, and they don't go to 0. And if it happened to be that both of them have positive measure, then it would not be ergodic.
Yeah, I think that would be the natural way to investigate it, like
Yeah.
to somehow partition this. Because C and all its previous is already full, but if I can somehow partition E to two sets that I can distinguish and find that they are both positive measure, then I can conclude it's not. That would be good.
I would get this, I guess it's ergodic, but maybe you can even, since you like bad guys, you can create a non-ergodic version.
Yeah, maybe if I put more care into like maybe the even numbered branches and put something there. Something like that.
Are there any other questions? Okay, let's thank the speaker again.